Imagine a massive corporate skyscraper at like 2 in the morning.
Okay.
The lights are blazing on every single floor. You've got thousands of emails flying back and forth. Massive data sets are being compiled. Code is being written, debugged, pushed to production.
Right.
Marketing campaigns are launching across all these different platforms. Basically, a massive amount of value is being generated in real time.
Right.
But, and here's the catch, if you were to walk through the front doors and take the elevator up to those floors, you wouldn't find a single human being sitting at a desk.
It's essentially a ghost ship, but a highly, highly productive one.
Exactly. And that is the exact image our source materials are painting for us today. Because if you've been following the tech world over the last few years, or, even if you just read mainstream headlines, you probably have this very specific, very solitary image in your head when someone says AI.
Yeah, the text box.
Right. You think of a chatbot, a solitary text box on a screen. You type a question, you get an answer. But the mission for this deep dive today is to unpack a comprehensive architectural blueprint based primarily on this thing called the Crew AI framework that proves that specific era of interaction is, well, it's already over. We're moving from pinging solitary assistants to building entire autonomous digital organizations. We're talking about a literal AI workforce.
Yeah, and the distinction there between, an assistant and a workforce, it represents a fundamental reimagining of how computing is even executed.
Right.
We're moving from a paradigm where humans use AI as a tool to a paradigm where humans actually manage AI as a team.
Manage them. Yeah.
And we're going to break this down today from the foundational raw code, like the absolute bedrock infrastructure, all the way up to what they call multi-agent orchestration.
Which is fascinating.
It really is. It's where multiple AI models speak to each other, evaluate each other's work, delegate subtasks, and deliver finished projects with virtually zero hand-holding.
Right. But before we get into the nuts and bolts of constructing this workforce, we really have to look at why the sources consider the old way obsolete.
Yeah, the shift.
They refer to this transition as the agentic paradigm shift. The materials draw this really sharp dividing line between what they call the co-pilot era and the new agentic era.
So the co-pilot era, right? It's built entirely on deterministic linear flows. You have a user prompt. That prompt is fed into a large language model, and the model generates a raw output. That's it. The machine does absolutely nothing until a human physically pushes a button.
It's essentially a highly advanced calculator.
Exactly.
The punch in the equation, you get the sum. If the sum is wrong because you typed the equation poorly, the calculator doesn't care.
No, it doesn't.
It just sits there and waits for you to type a new equation.
Yeah, right. The burden of quality rests entirely on the user's ability to craft the perfect prompt. The software doesn't plan. It doesn't reflect. It simply predicts the next most likely word based on your input, and it stops the absolute second it reaches the end of its generation cycle.
But the agentic era flow in these blueprints, it just shatters that linear process.
Oh, completely.
In this new model, you don't even talk directly to the AI that does the actual labor. You speak to an orchestrator agent.
The manager.
Right. You hand over an objective.
Yeah.
And the orchestrator takes that objective and loops the work between a specialized team. Like the diagram we're looking at highlights a research agent, a code agent, and a review agent.
Yeah, the loop.
They're passing a project back and forth in an iterative loop to create a polished output.
And the critical mechanism here, the really fascinating part, is the introduction of this autonomous evaluation loop.
How does that actually work?
Let's look at how it functions outside of the user's view. So a code agent writes a script based on the orchestrator's instructions. In the co-pilot era, that script goes straight to you. You have to check it.
Right.
In the agentic era, the code agent passes it to the review agent instead. The review agent runs a diagnostic, identifies, say, a syntax error, and sends it back to the code agent with a note saying, fix line 42.
Wow.
And this might happen 10 times in the span of 3 seconds, completely autonomously.
Okay, let me stop you there, because anyone who has worked in software development, or really any collaborative environment, knows that loops like that can become disastrous.
Oh, for sure.
Like, what stops the research agent and the review agent from getting trapped in an endless argument?
The infinite loop.
Yeah. If the review agent keeps rejecting the code and the code agent just keeps submitting the exact same flawed code over and over, I'm just sitting at my computer waiting for an output that is literally never going to come.
Yeah, and you've identified the primary vulnerability of early multi-agent systems right there. Infinite looping is a huge problem.
Right.
But this is exactly why the orchestrator agent is mandatory. The orchestrator doesn't just delegate work, it governs the context window and the iteration limits.
So it's actively watching them.
Yes. When the orchestrator assigns the task, it hardcodes a parameter called max iterations. It might set the limit at, let's say, 5.
Okay.
If the code agent and review agent cannot reach a consensus by the 5th loop, the orchestrator forces a halt. It evaluates the roadblock. Depending on its programming, it might lower the strictness of the review agent, or inject new contextual instructions, or even just flag the human manager for an intervention.
Oh, wow. So the orchestrator isn't just a dispatcher, it's an actual circuit breaker.
Exactly. It's an active supervisor maintaining the operational bounds of the whole system.
That's wild. Okay, so to build a system this complex, we really have to examine the infrastructure developers are using. The blueprints dedicate a massive section to the developer's foundation.
The digital concrete, so to speak.
Yeah, exactly. And at the absolute bottom layer, we have Python. The text refers to Python not as the AI itself, but as the versatile foundational glue.
Yeah, and Python's dominance here isn't an accident at all.
Why is that?
Well, AI models are essentially massive, incredibly complex mathematical matrices.
Right.
Interacting with them requires sending and receiving massive amounts of data through application programming interfaces or APIs.
Right, that connection.
And Python is incredibly efficient at network requests, data manipulation, and integrating disparate software libraries. It acts as the central nervous system connecting the different organs of our AI workforce.
Okay, so right above Python, the blueprint details the workspace layer. And it highlights two environments specifically, VS Code and Jupyter. It designates VS Code for local debugging, while Jupyter is for exploratory iteration. And I really want to understand the mechanical necessity of jumping between these two.
Right.
Like, why not just write all your code in one place?
It really comes down to the nature of how AI development actually works in practice. Traditional software development is highly structured. You write a program, you compile it, you run it.
Right.
But AI development is highly experimental. Jupyter Notebooks allow you to run Python code in these isolated little cells.
Cells.
Yeah, like blocks. You can execute 3 lines of code, leave the results sitting in memory, and immediately write 3 more lines to interact with those results without having to run the whole entire program all over again.
Oh, I see. So it's basically a scratch pad.
Exactly.
You are testing if the logic actually holds before you commit to building the whole structure around it.
But once you validate that the logic holds, a scratch pad becomes a liability.
Right, because it's messy.
Super messy. You can't manage a deployment with thousands of files and complex dependencies in a Jupyter notebook.
Yeah, that would be a nightmare.
So you move to VS Code, which is a full-fledged integrated development environment. It provides robust tools for version control, deep debugging, and actually managing the architecture of a massive project.
Okay, that makes sense. But the blueprints also make it clear that the really heavy lifting doesn't happen in either of those local environments.
No, not at all.
The next block in the architecture is Google Colab, specifically utilized to access Cloud GPU's graphics processing units, like the NVIDIA V100 or the A100.
Yeah, the big guns.
Right. So why GPUs? Why can't the standard processor inside my laptop just handle this?
So a standard central processing unit, or CPU, is designed to execute a few complex tasks very, very quickly in sequence. Think of it like a sports car.
Okay.
A GPU, on the other hand, is designed to execute thousands of really simple mathematical operations simultaneously. It's like a massive freight train.
A freight train versus sports car, got it.
And large language models process language by breaking words down into numerical tokens and running them through billions of neural network parameters. That requires massive parallel processing. The NVIDIA A100 is specifically architected for these tensor operations.
And most developers definitely don't have an A100 just sitting on their desk.
Oh, they don't, because a single A100 can cost upwards of $10,000.
Wow.
Yeah. So Google Colab solves this compute bottleneck. It provides a cloud-based portal where a developer can write code in their web browser, but that code is actually executing on a massive server rack of A100s sitting in some Google data center.
That's incredible. So it democratizes access to that power.
Exactly.
And the final piece of this foundational layer is the model repository, specifically calling out Hugging Face. The text describes this as a space for quick experimentation with open source models via inference APIs.
Right. So Hugging Face functions somewhat similarly to GitHub, but specifically for AI models.
Okay.
You don't have to train an intelligence from scratch, which would cost millions. You can just browse Hugging Face, find an open source model trained by Meta or Mistral, and download its weights directly into your Google Colab environment.
So the combination of Python, cloud GPUs, and open source repositories means an individual developer right now has access to the kind of computational infrastructure that was literally exclusive to nation states and tech giants just a decade ago.
It's an unprecedented shift in capability.
Unbelievable. Okay, so we have our infrastructure. The factory floor is built and powered. Now we have to source the actual intelligence, the large language models that will serve as the brains for our agents.
The fun part.
Right. The source material presents a pretty complex LLM sourcing strategy matrix. It evaluates models based on setup, privacy, and scalability.
And I should say, this matrix is the single most important strategic decision a company will make when architecting an AI workforce.
Real, the single most important.
Absolutely. It dictates your operational limits, your financial burn rate, and your legal compliance.
Wow, okay. Well, the matrix gives us three options. Option one is utilizing LLM APIs, pointing to commercial models like OpenAI's GPT-4 or Anthropic's Claude. The setup is marked as the fastest. You pay per token, and you have massive scalability.
Yes.
But the glaring warning label here is potential data privacy limitations.
Yes.
Let's break down the mechanics of an API call to understand that warning, because I think a lot of people overlook that.
It gets overlooked all the time. So when your agent uses an API, your application is literally packaging your data and sending it over the public internet to the provider's servers.
Over the public internet.
Yes. The provider's model processes the data and sends the response back. Now, if your workforce is just analyzing public marketing trends, this is highly efficient and totally fine.
Right. Who cares if that leaks?
Exactly. But if your workforce is analyzing proprietary source code or unreleased financial earnings, you are transmitting highly sensitive data to a third party.
And even if the provider promises they don't train on your data, the data is still leaving your localized environment.
And that's a hard stop for a lot of industries.
Right, which brings us to option two. Cloud services like Azure or AWS. The setup here is vastly more complex. It requires dedicated infrastructure engineering, but it offers enterprise-grade compliance.
Yeah, this is what we call the walled garden approach.
The wall of the
A
garden.
massive corporation will basically rent an isolated segment of AWS. They deploy the AI models entirely within their own secure virtual network.
So the data never leaves.
The data never travels across the public internet to a consumer API. It remains completely bounded by enterprise security protocols. It is incredibly scalable, but you are paying a massive premium for the infrastructure, not just the token usage.
So it's expensive but secure.
Mm.
Then we have option three, which is kind of the total opposite of the API approach. Local models.
Right.
This involves running models like a llama or open source downloads from Hugging Face directly on your own physical hardware. The matrix lists the benefits as utmost privacy and security and zero latency because the data never leaves the room. But wait, earlier we established that local machines can't handle the compute required for AI. We needed Google Colab. So how does this actually work for a business?
It works through sheer massive capital expenditure.
Oh, buying the hardware.
Right. To achieve the zero latency promised by local models at scale, you aren't running this on a laptop. You are purchasing and maintaining your own physical server racks.
So you're building your own data center.
Exactly. You are buying those $10,000 NVIDIA GPUs yourself,
Right.
setting up the liquid cooling systems, hiring the network engineers.
That sounds incredibly expensive.
It is. And beyond the hardware cost, there is a severe scalability boundary.
What do you mean?
Well, think about it. If your AI workforce relies on an OpenAI API and suddenly experiences a, say, 500% spike in workload.
Like a viral event.
Exactly. OpenAI's massive server farms automatically absorb that load. You just pay a slightly higher token bill that month.
Right.
But if your local model experiences a 500% spike, your servers just crash. You cannot scale beyond the physical metal actually sitting in your server room.
Wow. Okay. So this matrix forces you to really identify your absolute non-negotiables.
Totally.
Like if you are a healthcare provider dealing with protected patient health information, an API is just a regulatory violation right out of the gate.
It's illegal.
You are forced into cloud services or local models, regardless of how complex the setup is or the hardware costs. But the blueprints do introduce a concept called model agnosticism within the Crew AI framework to alleviate some of this pressure.
Yeah, and model agnosticism is a really brilliant architectural feature. It basically means the orchestrator doesn't care what brand of brain an agent uses.
Doesn't care.
No, the framework just translates the communication for them.
Oh, so you can mix and match.
Precisely. So if your workforce has a research agent pulling public articles from the web, You can power that specific agent with a cheap, fast API like OpenAI.
Okay.
But if that data is then passed to a financial analysis agent that handles your company's private ledger, you can power that specific agent with a highly secure, local open source model.
That is so smart.
The framework allows them to collaborate seamlessly, so you're optimizing for both cost and privacy simultaneously.
That's a game changer.
Yeah.
Okay, so we've selected our models. We have the raw intelligence, but out of the box, an LLM only possesses general knowledge, right?
Right.
It knows a little bit about everything up until its training cutoff date. To make an AI workforce actually valuable to a specific business, you have to educate the models on your specific proprietary data.
You have to give them the company handbook, basically.
Duh, exactly. And the sources highlight two fundamentally different methods for this: fine-tuning and RAG.
RAG, which stands for Retrieval-Augmented Generation.
Right.
And you're entirely correct to separate these two methodologies. They're often conflated in mainstream discussions, like people use the terms interchangeably, but mathematically and operationally, they're entirely distinct things.
Let's start with fine-tuning. The visual in the blueprint shows a neural network undergoing weight alteration and internal pathway modification. When we say we are altering the weights, what are we mechanically doing to the AI?
So a large language model is essentially a massive web of mathematical probabilities.
Right.
When it learns a concept, it adjusts the numeric weights between its artificial neurons. So if you want a model to stop speaking casually and start speaking in strict, formal legal terminology, you fine-tune it.
Okay.
You feed it thousands of examples of legal documents. The model uses a process called backpropagation to continuously recalculate and adjust billions of internal weights until its default baseline predictive state naturally outputs legal jargon.
It fundamentally changes how his brain works.
Yes.
But the source material is very clear about the drawbacks here. It is highly resource-intensive, requiring immense GPU compute time. And more importantly, it results in a fixed knowledge base with a strict cutoff date.
And that is the crucial limitation of fine-tuning. It permanently alters the internal structure. Think of it like baking a cake.
Baking a cake.
Once the cake is baked, you cannot easily remove an ingredient. If you fine-tune a model on your company's product catalog on a Monday, and then you discontinue a product on Tuesday, the AI doesn't know that.
It still thinks it exists.
It will confidently hallucinate that the product still exists because that fact is literally hard-coded into its neural weights.
Wow.
Retraining it to forget that product requires another massive expenditure of compute time. You have to bake a whole new cake.
That sounds incredibly inefficient for a fast-moving business.
It is.
Let's contrast that with the visual for AG. It shows the neural network, but its weights are untouched. Instead, the network is connected to an external entity labeled a vector database, and the process is called real-time context injection.
Right. This is where we shift from altering the brain to providing the brain with a reference library.
I really need to understand this vector database concept because the blueprint emphasizes it so heavily.
Sure.
How do you turn a company's internal documents, like PDFs, HR policies, technical manuals, into something an AI can actually actively retrieve?
You use something called an embedding model.
An embedding model.
An embedding model takes a chunk of text, say, a paragraph from your HR manual, and translates the semantic meaning of that paragraph into a long string of numbers. These numbers represent coordinates in a multi-dimensional space, and that set of coordinates is a vector.
So it's basically mapping concepts geographically.
Exactly. Words with similar meanings are plotted close to each other in this high-dimensional space.
So like puppy and dog will have coordinates very close together.
Right. And puppy and carburetor will be plotted very far apart.
That makes sense.
So when a user asks a question, the RAG system translates the user's question into a vector as well. It then searches the vector database for the text chunks that are mathematically closest to the question's coordinates.
Oh, wow. So if I ask my AI workforce, what is our company policy on remote work? It doesn't even try to answer from its general memory.
Nope.
The system searches the vector database, finds a specific paragraph in the proprietary HR manual about remote work, and then injects that paragraph directly into the prompt alongside my question.
Yes. The system effectively says to the LLM, using only the information provided in this retrieved paragraph, answer the user's question.
Real-time context injection.
Exactly. The LLM is acting purely as a reasoning engine in this scenario, applying its linguistic capabilities to the exact up-to-date facts that you just handed it.
It's like the difference between studying for 10 years to become a doctor versus giving a highly intelligent person a medical textbook and just asking them to find the answer on page 42.
That is a perfect analogy. Fine-tuning alters the fundamental intuition of the machine. RGAG gives an unchanged machine a dynamically updating filing cabinet.
And because RI relies on an external database, updating the AI's knowledge is trivial, right?
Incredibly trivial. If you discontinue a product, you simply delete that product's text file from the vector database.
Yeah, it's gone.
The AI instantly stops referencing it because the file isn't there to retrieve anymore. RA introduces a very slight latency because of that retrieval step, but it guarantees accuracy and pretty much eliminates the hallucination problem inherent to static models.
So in enterprise architecture, RA is the gold standard for knowledge management.
Yes, while fine-tuning is reserved strictly for altering a model's overarching behavior or tone.
Okay, this is all coming together.
Yeah.
We have poured the digital concrete, we have selected our models, we've integrated our vector databases for knowledge retrieval. Now we arrive at the absolute core of the blueprint, the crew AI paradigm.
This is where it gets really fun.
How do we take all these isolated components and actually architect a workforce?
So the Crew AI framework operates by mapping these deeply complex software engineering principles onto familiar, everyday organizational concepts.
Right.
It creates an abstraction layer that humans can actually understand.
And the mapping is so direct. The blueprint states, agents are employees, tasks are assignments, crews are departments.
Exactly.
Let's examine the anatomy of an agent. When a developer instantiates an agent in Python, they aren't just writing an open-ended prompt. They configure rigid parameters. Every agent requires a role, a goal, and a backstory. Now, role and goal are straightforward. The role might be senior financial analyst, and the goal might be identify cost-saving opportunities in Q3 data.
Right. Standard corporate stuff.
But the backstory parameters, what I really want to challenge here.
Okay, let's hear it.
The example given in the text is for a writer agent, and it says, creative and persuasive, you have spent a decade crafting content that resonates with tech audiences. Why does a piece of Python code need a creative writing backstory? We are building enterprise software, not directing community theater. This just feels like anthropomorphizing the machine unnecessarily.
I totally get why you'd say that. It absolutely sounds like theatrical flavor text. But the mechanical reality of how large language models process information makes the backstory mathematically critical.
Mathematically critical. How?
Well, we have to go back to how these models work. They are probability engines operating within a limited context window.
And the context window is the total amount of text the model can, like, see and consider at any given moment while it's generating an answer.
Correct. The system prompt, which includes the role, the goal, and the backstory, is pinned to the very top of that context window. Every single autonomous decision the agent makes must pass through the filter of that backstory.
Okay.
If you just give an agent the role of analyst, the probability engine has a massive, completely unfocused range of possible vocabularies and methodologies it could draw upon.
Right. It could act like a psychological analyst, a sports analyst, or a data analyst. Has no idea.
Exactly. By providing a rich, detailed backstory, you are mathematically bounding the probability engine. You are forcing the attention mechanism of the neural network to weigh specific concepts more heavily.
Oh, I see.
If the backstory says, you are a conservative financial analyst who strictly relies on GAAP principles and avoids speculative investments, the statistical probability of the AI hallucinating a recommendation to buy a volatile cryptocurrency drops to near absolute zero.
Because those words don't align with the probabilities of a conservative GAAP analyst.
Exactly. The backstory isn't role play. It is a rigid behavioral constraint.
It prevents the agent from stepping outside of its defined operational parameters.
Yes.
Wow, okay, that completely reframes it for me. Now, along with the backstory, the anatomy of an agent also includes specific tools.
Yes, tools are vital.
Tools bridge the gap between a language model and the outside world. Right. Because an LLM on its own can only generate text. It can't browse the internet, it can't read a database, it can't execute code.
Right, it's trapped in a box.
But the Crew AI framework equips agents with specific Python functions, like a scrape website tool gives the agent the ability to pull raw HTML from a URL. A SQL query tool gives it the ability to read a database.
So you are basically handing the digital employee a specific set of equipment.
And then you hand them a task.
Right.
The blueprints really emphasize explicit execution for tasks. You can't just tell the agent to do some research. The parameters require you to dictate the exact expected output format. There's a toggle shown in the code called output_JSON.
Yeah, and understanding the necessity of JSON formatting is critical to understanding how multi-agent workflows even function.
What is JSON exactly for people who don't code?
JSON stands for JavaScript Object Notation. It is a highly structured way of organizing data into key value pairs. Think of it like a very strict spreadsheet format, but written in text.
But why can't the agents just pass natural text documents back and forth?
What do you mean?
Well, if the research agent finds some great data, why not just send a normal paragraph of text over to the data analyst agent?
Because natural language is inherently ambiguous, humans are good at inferring things, computers aren't. If the research agent writes a paragraph saying, the company's revenue increased by 20% to $5 million, but user growth slowed down significantly in the EU, the data analyst agent has to read that sentence, parse it, infer the context, extract the numbers, and just hope it doesn't misunderstand what slowed down actually means in this specific context.
It introduces a massive margin for error.
A huge margin. But if the research agent is forced by the orchestrator to output its findings in strict JSON format, the output looks like code.
Right.
It outputs revenue increase 20%, total revenue 500,000, user growth declining.
There's zero ambiguity there.
Exactly. The next agent in the pipeline can programmatically ingest that exact data point without having to interpret the nuances of human language. Strict formatting guarantees that the baton can be passed between machines without dropping the data.
Okay, this brings us to what I think is the most mind-bending part of the entire blueprint, the cognitive layer.
Oh, this is where it feels like sci-fi.
It really does, because we have specialized agents passing perfectly formatted data. But these sources point out a massive flaw in standard AI, which is amnesia.
Yes.
If an agent forgets everything it did 5 minutes ago, the whole workforce collapses.
Of course.
The Crew AI framework introduces a 4-tiered memory architecture to solve this. Let's start with short-term memory.
So short-term memory is the immediate operational buffer. It allows the agent to maintain continuity within an active execution loop. If the code agent is going back and forth with the review agent, short-term memory ensures the code agent actually remembers the specific error the review agent pointed out 2 minutes ago, so it doesn't just make the exact same mistake in the next iteration.
So it remembers the conversation it's currently having. But once the task is completely finished and the agents are shut down for the day, that short-term memory is wiped.
Right, it's cleared out.
But long-term memory persists. The blueprint states long-term memory accumulates wisdom from past executions to continually refine future decision-making. How is that mechanically stored?
Long-term memory is essentially a dynamic feedback loop integrated with a vector database that we talked about earlier.
Okay.
When an agent successfully completes a complex task, or maybe it successfully resolves an error after multiple failures, the orchestrator logs that operational pathway into the database.
It saves its work.
Yes. So weeks later, if the agent faces a structurally similar problem, it retrieves that past success from its long-term memory and applies the learned methodology. The system actually becomes more efficient the longer it runs.
It learns from experience.
Literally.
Then we have entity memory. This categorizes specific facts about people, places, and persistent concepts. And I think this is profound.
It's massive for customer service.
Because if you think about the software as a service model right now, every time I open a new chat window with a standard AI, it's a blank slate.
Completely blank.
I have to re-explain who I am, what my company does, what my preferences are. Entity memory changes that entirely.
Entity memory builds a permanent relational graph.
How does that work?
Say your AI workforce is managing customer success. The first time a client named Sarah emails about a software bug, the system creates an entity profile for Sarah. It notes her technical proficiency, her company, her typical tone.
Okay.
6 months later, if Sarah emails again with a completely different question, the agent pulls the entity memory. It instantly remembers her, realizes she is a highly technical user, and adjusts its communication style to bypass all the basic, annoying troubleshooting steps.
Have you tried turning it off and on again?
Exactly. It skips that because it knows she already knows that.
It mimics genuine human rapport. The AI isn't just processing a ticket, it's recognizing a relationship.
It changes the entire feel of the interaction.
And finally, the blueprint details contextual memory, which integrates the other 3 memory types to maintain a consistent narrative thread.
Think of contextual memory as the overarching compass for a massive project. If the orchestrator assigns a crew to write a 300-page technical manual, that project might take thousands of individual subtasks to complete over several days.
Right. Researching Chapter 1, drafting Chapter 2, reviewing Chapter 3.
Without contextual memory, the agent drafting Chapter 20 might lose track of the core theme established way back in Chapter 1.
It would just wander off.
It might drift off topic or change its writing style entirely. Contextual memory constantly pulls the short-term task data, the long-term stylistic guidelines, and the entity definitions of the target audience to ensure that every single agent's output aligns with the project's macro objective.
It prevents the workforce from losing the forest for the trees.
Precisely.
Okay, so we have our educated, highly specialized employees with perfect memories. But if you throw 50 brilliant people into a room without a management structure, you don't get a product, you get chaos.
Absolute chaos.
The blueprints outline two primary architectural flows for orchestrating the crew: sequential flow and hierarchical flow.
And this is where we really transition from agent design to process engineering. The choice between sequential and hierarchical dictates the fundamental agility of your entire system.
The sequential flow is visually very simple in the diagram. It's just a straight line. Agent A finishes their work, hands it to Agent B. Agent B finishes, hands it to Agent C. The text calls it a strict linear relay race, guaranteeing a fixed order of execution. It is entirely deterministic.
Right. Sequential architecture is utilized when the input is highly predictable and the required transformations are rigid. Agent B physically cannot initiate its process until Agent A provides the specific output.
So it's locked in.
It prevents race conditions and ensures data integrity for pipelines that just must follow a specific logical order.
The hierarchical flow, however, looks exactly like a corporate org chart. At the top sits a manager node, with arrows pointing down to various specialists. The blueprint describes this as dynamic delegation and validation.
In a hierarchical setup, the orchestrator evaluates the incoming objective and actively decides which agents are required. The execution path is not predetermined. It is formulated in real time based on a semantic analysis of the prompt.
So if I am a user or a developer building an AI workforce today, what dictates my choice between these two flows? Like, when do I use a relay race and when do I hire a digital manager?
It entirely depends on the variability of the problem you are solving.
Okay.
If you are building a system to process daily inventory logs and generate a nightly restock report, the steps never change. Read the database, calculate the deficits, format the PDF.
Right. Same thing every night.
Sequential flow is highly efficient for that and far less prone to edge case failures. But if you are building an AI workforce to handle a chaotic inbox of unformatted customer emails, you need a manager.
Because you don't know what's coming.
Exactly. You need a system that can look at an email, realize it contains both a billing question and a technical glitch, and dynamically delegate those subtasks to the appropriate specialists simultaneously.
That makes perfect sense, and that actually sets us up perfectly to look at the three real-world architectures provided in the sources. This is where the theory translates into functioning businesses.
Let's see them.
Let's examine Architecture 1, Financial Planning.
Okay, this architecture is a textbook example of strict sequential process. Financial planning requires linear data refinement.
The flow maps out like this. The user inputs their raw financial data, income, debts, savings goals. This data goes to the budgeting agent. The budgeting agent isolates discretionary income and essential expenses. It then passes that structured data to the investment advisor agent. That agent calculates risk tolerance and recommends specific ETFs. Then it goes to the debt management agent, which structures a payoff plan for high-interest loans. Finally, a document agent compiles it all into a comprehensive financial plan.
And the sequential rigidity there is the entire point.
Because if it went out of order, it'd be a mess.
If you used a hierarchical flow here, the investment advisor agent might try to recommend stock purchases before the debt management agent had calculated how much money was actually bleeding out through credit card interest.
Oh, yikes.
The strict linear flow enforces logical financial priority.
That makes sense. But Architecture 2 shifts gears entirely. This outlines a product launch crew, and it introduces a massive new mechanism that changes the safety profile of the entire system.
Yes, this architecture is built around content generation, which inherently carries public-facing risk.
Right. The flow starts with a market researcher agent. It utilizes tools to scrape competitors' websites and pull trending keywords. It formats this research into a rigid JSON file. It passes that JSON to the content creator agent, who drafts a series of blog posts and marketing emails. But the arrow doesn't proceed to the PR specialist agent who publishes the content. The arrow hits a block labeled the Human Input Required Validation toggle.
This is the human-in-the-loop mechanism, and it is absolutely vital for enterprise deployment.
Why is that?
Because an autonomous AI loop can operate at incredible speeds, which means it can make catastrophic mistakes at incredible speeds.
Right.
If the content creator agent hallucinated a false claim about a competitor and the system is fully autonomous, that claim gets published to thousands of subscribers instantly.
Before anyone even notices.
Exactly. The validation toggle acts as a hard pause. The entire multi-agent system suspends execution. It sends the drafted content to a human manager's dashboard.
Okay.
The human reviews the text. If it looks good, they click approve, and the PR specialist agent takes over to publish it.
But what if it's bad?
If it's flawed, the human can type in feedback. The tone is too aggressive. Rewrite this to focus on our features, not the competitor's flaws. The orchestrator ingests that human feedback, passes it back down to the content creator, and the loop begins again.
That's a huge relief. We aren't just letting the machines run the whole launch blindly.
No, it allows you to leverage the immense speed of AI for 99% of the heavy lifting. The research, the drafting, the formatting, while retaining absolute human veto power over the final 1% of execution.
That's the perfect balance. Finally, we have Architecture 3, the call center. This is our blueprint for hierarchical routing in a highly unpredictable environment.
Yeah, customer service is inherently chaotic. Users don't submit perfectly formatted JSON requests. They write angry, confusing, multi-part emails.
Oh, I know. The org chart here features a customer service manager, the orchestrator at the top. Below it are 4 specialists, a call handling agent, a tech support agent, a billing agent, and a customer feedback agent. When a ticket comes in that says, I was overcharged on my last invoice and also your app keeps crashing on my phone, how does the manager node handle that dynamically?
The orchestrator first performs semantic analysis on the text to identify the core intents. It recognizes the billing intent and the technical intent.
Okay.
Instead of sending the ticket down a linear pipeline, the orchestrator splits the task. It delegates the invoice issue to the billing agent, granting it access to the SQL database tool to check the user's account. Simultaneously, it delegates the crash issue to the tech support agent, providing it with the device data.
So they are working in parallel.
Exactly. Once both agents resolve their respective issues, they send their outputs back up to the orchestrator. The orchestrator synthesizes the 2 technical responses into a single, cohesive, polite email and sends it back to the customer.
It's triage, delegation, and synthesis, all happening in a fraction of a second.
That's remarkable.
It really is. And this brings us to the final visual in the source material, a complete synthesis diagram appropriately titled The Complete AI Agents of Architecture.
Oh.
It stacks every single concept we've discussed today into one cohesive tech stack.
Let's trace it from the bottom up.
Okay.
At the absolute bedrock, we have the development environment and Python. This is the local VS Code environment, the Jupyter Notebooks, and the cloud-based Google Colab GPUs providing the raw compute power.
Sitting directly on top of that compute power is the intelligence and context layer.
Right.
This is the strategic choice we made earlier. It houses your large language models, whether that is a high-speed OpenAI API or a highly secure local model intertwined with your vector databases running RA to provide proprietary real-time context.
And the foundational hardware and the intelligence models form the raw capability of the system. But the next layer up is the CrewAI framework itself. This is where capability is shaped into utility. This layer houses the orchestrator, the individual agents with their specific roles and backstories, the tools they use to interact with the world, and the sophisticated 4-tiered cognitive memory system that tracks all their progress.
And finally, at the very top of the stack, emerging from all of this orchestrated complexity, is the final structured output.
Yes.
The finished financial plan, the approved marketing campaign, or the resolved customer service ticket. The source material distills this entire diagram down into one definitive thesis.
Yeah.
Building agents is designing digital organizations. Infrastructure provides raw capability, but orchestration provides the intelligence.
That sums it up perfectly. A $10,000 NVIDIA GPU and an advanced language model are incredibly powerful pieces of technology, but on their own, they are inert. They just sit and wait for a prompt. The intelligence of the new era doesn't come from a single smarter AI model. It comes from the architecture of collaboration.
It comes from giving these models constraints, tools, memory, and a management structure that allows them to evaluate, iterate, and execute autonomously.
Exactly.
We have fundamentally moved from an era of solitary one-on-one interaction to an era of systemic multi-agent collaboration. The co-pilot is being replaced by the agency.
It's a new world.
It really is. We've covered an immense amount of technical architecture today, from the mechanics of probability engines and vector databases to the organizational flows of hierarchical management. But I want to leave you with a final thought to mull over, something that isn't drawn on any of these diagrams, but is the undeniable logical conclusion of everything we've unpacked today.
Let's hear it.
If the future of software development is no longer about writing linear loops of code, but is instead entirely about designing digital organizations, complete with specialized employee agents, department crews, active manager nodes, and human-in-the-loop review systems, what does that make you? You are no longer just an end user typing a prompt into a chat box. You aren't even just a programmer debugging a script. The tools are democratized. The infrastructure is accessible. You are now the architect, the manager, and essentially the CEO of a digital company that operates at the speed of compute and never sleeps.
Wow.
You have an entire workforce waiting in the cloud, capable of researching, coding, reviewing, and launching complex products. The question isn't whether the technology is capable of running the organization. The blueprints we've explored today prove that the architecture is already here. The question is, now that you have the workforce, what are you going to assign them to build tomorrow? Thanks for joining us on this deep dive. We'll catch you on the next one.